In this video, we're going to be talking about acids and bases. Now, this is going to be a multi-part video series where we're going to be looking at and studying acid bases and their equilibriums and learning how to calculate the pH, pOH, and of strong acids, strong bases, weak acids, and weak bases. So in this video, we're just going to introduce what an acid base are, and we're going to talk about calculating pH of strong acids and just get a basic firm understanding of what an acid is. So before we get started with that, we always have to think about where have we encountered an acid or base. And we live our lives every day. We use acids and bases all around us. Our body's pH is maintained by an acid base. And so, these are just examples that I have at my house. And if we look at the leftmost picture here, you'll see that we have Pine Glo, we have Scent-Away, which is a laundry detergent. We have Palmolive behind it. These are all soaps, and soap itself is slippery. It cleans stuff very well, and that's considered to be a base. Now, some common examples of acids are found on the bottom right hand picture, and you see the vinegar behind it, you see the muriatic acid. These are all things that you can buy in the store, and then you see your fruits and your vegetables below. And so, acids and bases are all around us. Now, there's one question I'm going to ask you, and I'm going to give you about 5 or 10 seconds to answer this question. Is milk considered an acid or a base? You should be thinking of an answer. What do you think it is? All right, so that was 10 seconds. Milk is considered to be acidic. It's most commonly thought to be a basic compound. We talk about you drink milk before you go to bed. A lot of people do. I also do as well. And that's not because of it being a basic or acidic compound. It's just because it helps you to go to sleep easier. Now, milk is acidic because it has lactic acid in it. And if you've ever been lactose intolerant, you're lactose intolerant because you don't have the enzyme to break down the lactose that's present, and that's what makes milk partially acidic. In fact, milk is 6.8 on the pH scale. So, interesting fact. Now, what is an acid and a base? So there are 3 definitions that define an acid and a base. We're only going to focus on 2 of those in this video. The first one is Arrhenius' definition of an acid and a base. Now, Arrhenius states that an acid will produce a hydrogen ion and a base will produce a hydroxide ion. Now, for future note, we call hydrogen ions protons because they lack an electron, and the only thing they do have are protons present. Hydroxide ions are represented by the OH with a -1 charge. Number 2 definition here is Bronsted-Lowry. Bronsted-Lowry defines an acid as a proton donor and a base as a proton acceptor. Now, not everything classifies and falls underneath both definitions, and so that's why there's multiple definitions that define acids and bases. And so one of the things we look at with a Bronsted-Lowry is the fact that it can accept a proton, in this case a hydrogen, or it can donate. So if we talk about HCl, for example, HCl has a hydrogen ion, and what will happen is it will donate this hydrogen ion to a base. And you say, well, what's an example of a base? Well, a good example of a base would be NH3. So NH3, and this is where the Lewis structure comes back into play, NH3 has this lone pair up on top. And so if a compound has a lone pair, most likely it could be a basic compound, because what will happen is this hydrogen will attach here. So the NH3 compound will accept the hydrogen from the HCl. And so if we talk about, NH3 into water, all right, now water is unique. We're going to talk about water in just a little bit, but water itself can act as both an acid and a base. So when you put NH3 into water, what will happen here is that the hydrogen from water is going to be donated to NH3 because NH3 is a basic compound. So NH3 is a base. Now what that tells you is that water then is considered to be an acid. So you form NH4 plus 1 because you're donating that hydrogen. And remember, the hydrogen has a plus 1 charge, and it bonds to the nitrogen, which causes it to form an overall plus 1 charge. And this would be ammonium. Now, the result of that is that the hydrogen then loses its electron to the oxygen, and so you form a hydroxide. Now, when we work with Bronsted-Lowry, we also have to think about conjugates here because we're going to form a conjugate base and a conjugate acid. So when we look at the NH3 being a base, well, NH4 is the opposite of it, so you form this pair, and that means that the NH4 plus 1 is a conjugate acid. Now, that also tells me that the water is going to be pairing up with the hydroxide, and the hydroxide is a conjugate base. So one of the things that I've always found interesting is that if you go to the store and you buy a bottle of ammonia, well, it says ammonia on the front. Now here's what the fun part is. Flip it around and look at the ingredients of that bottle. It does not say the ingredients are of ammonia. It says the ingredients are ammonium hydroxide. And and that's really going back to what we're seeing here in this example here. The ammonium hydroxide over time will break down to form the ammonia plus water. You know that if you've ever had ammonia, it eventually will break down and it becomes less concentrated over time, and so you have to buy new ammonia to replenish that. Now let's talk about water. So we talked about water being weird in that water has its own unique equilibrium. Water, you can see it here, but I'm going to draw it right below. So water in liquid form breaks down to produce hydrogen ions plus hydroxide ions. And we just talked about equilibrium in the previous chapter, and so we can write in the expression here where we have the Kw is equal to the hydrogen concentration times the hydroxide concentration. Now at 25 degrees Celsius, the Kw is equal to 1 times 10 to the negative 14. So when we are at 25 degrees Celsius, the pH of water should be 7, right? It should be neutral. And so water itself can go either direction. If it's amphiprotic, in other words, water can act as an acid, and water can act as a base. Right? So amphoteric is the word that we use for that. So amphoteric means it can act as both an acid or a basic compound. Not everything responds the same manner. HCl is a good example. HCl is only going to be an acid. It's never going to be a basic compound. Water could be an acid or a base depending on the situation and what you put into the solution. And so a lot of what we learn and what we use here is we base it around this equilibrium. And so anytime you're working at 25 degrees Celsius, you know the water's dissociation constant is 1 times 10 to the negative 14. If it changes, then your constant will change, but in most cases, that's not going to happen. So if the temperature is not specified in a question or problem, you can assume and be safe to know that you're working at 25 degrees Celsius, and the same equation applies. So when we talk about acids, we have to understand that there's a difference between a strong and a weak acid. Strong acids are going to dissociate completely, and then a weak acid will dissociate partially. So what does that mean? Well, when we write out the reactions, so let's say we have a strong acid, HCl. HCl will break down to form H plus Cl minus. Weak acid would be an example of, let's say, acetic acid, so it's just CH3, CO2, H. So it forms an equilibrium because it doesn't break down completely. It forms CH3, CO2 minus plus H plus. So this equilibrium suggests that we're working with a weak acid. A strong acid's different because a strong acid breaks down completely, so you're left with a full ionization of the acid. And what's important about this is that when we get into calculating the pH of strong acids and weak acids, we have to understand that whatever the concentration for the HCl is also going to be the concentration of the hydrogen ion, because it's a 1-to-1 ratio here. Now, yes, we have a 1-to-1 ratio here of acetic acid to the hydrogen ions, but that doesn't mean that we're going to form the same concentration of hydrogen ions, because you have this equilibrium. And when we're working with an equilibrium, we have to go back to our equilibrium chapter and calculating using the equilibrium expression for a weak acid. But for a strong acid, it's a whole lot easier. So what are the strong acids? So there are 8 strong acids. I suggest you memorize these or have this chart handy. This is an important chart because this is what helps you to determine the difference of how you calculate the pH of a solution. Now, in order for us to calculate the pH of a solution, we have to learn some basic equations to do that. We've already talked about the first equation, which was the Kw equation. All right, so Kw is equal to the concentration of hydrogen ion times the concentration of the hydroxide ion, which is equal to 1 times 10 to the negative 14 power. So stemming from that is the hydrogen concentration. The hydrogen concentration is equal to 1 times 10 to the negative 14 divided by the hydroxide concentration. Now, if you don't know the hydroxide concentration, well, it depends on the question. Most likely, since we're working with strong acid, we ain't got to worry about the hydroxide concentration. So, as we were talking about the dissociation of water, and we calculate the concentration of hydrogen ions, we need to know the hydroxide concentration. But if we're dealing with a strong acid, we won't know that because we're dealing with strong acids. So we need another equation. That equation is pH is equal to the negative log of the concentration of hydrogen ions. Now, we talked about a few minutes ago that a strong acid is something that dissociates completely. We see that we have 8 strong acids. So let's say that we know the concentration of HCl. Let's say that we have a 0.1 molar concentration of HCl. So if we want to calculate the pH, the first thing you have to understand is you have to know that you're working with a strong acid. That's why I said you have to memorize this, or you have to have this table. Second thing we have to do is we have to know which equation to use. Now, so in order to do that, we look at the HCl. HCl is strong acid. It breaks down to form H plus and Cl minus. The concentration of the H plus is equal to the concentration of the HCl. So now what we can say is the concentration of hydrogen ions are and is 0.1 molar. So to figure out the pH of the solution, all we got to do now is take pH is equal to negative log of 0.1 molar. So plug that in and make sure you do not forget the negative log. And what we end up with is 1.0 for that pH. Now, the second thing we want to do before we move on is let's talk about the significant figures aspect of this. So anytime you're dealing with calculating pH, you have to focus on what this number represents. So 1.0, if I were to ask you how many significant figures, you would most likely say that is 2 sig figs. But the answer is actually 1 sig fig, and you have to really understand why. So the first thing here is that this here, the first number, is your mantissa. The second number is your character. The mantissa is a placeholder, so it's basically like a scientific notation. It's just a placeholder. P stands for power because of the exponential form that it might be found in. And so when you write 0.1 molar, that is really 1 times 10 to the negative 1 molar. So this 1 that you see for the mantissa comes from that negative 1 exponent. So that is not, you don't count that as a significant figure. What you do count is the 1. The 1 is the significant figure here. So it's only 1 sig fig. So we look at the character for significant figures. So since this problem, since 0.1 molar only has 1 significant figure, the character is what's going to be your significant figure. 0 represents 1 significant figure, so that's why the answer is 1.0. If you wrote just 1 by itself, you're wrong if you're basing off sig figs, because you have to have the character. The character is where you get your significant figures from. So be very careful when assigning your significant figures. So let's say we have a solution of 0.25 molar H2SO4. Now this is a different type of acid. It is a strong acid, but it's a diprotic acid. So when you look at that list of 8 strong acids, you have 7 of them being monoprotic. Mono meaning there's only 1 hydrogen ion. H2SO4 is a diprotic acid. Now, that doesn't mean that both hydrogens on there are strong. What happens here with H2SO4, H2SO4 will release its first hydrogen, and its first hydrogen will be a strong acid. So H2SO4 is a strong acid. Now, being diprotic, you have a second hydrogen that comes off, and you form the sulfate ion as a result of this. And so this is a weak acid. So this is not going to be played into calculating the pH of the solution. All we're focused on is the first hydrogen that comes off of H2SO4. So that means that we're going to be working the same equation. So that means the concentration of the hydrogen ion is going to be equal to 0.25 molar, because this is a 1-to-1 ratio. So the pH is equal to negative log of 0.25 molar. And so what you end up with there, after you do the calculation, you will have a pH of 0.60. Now 0.25 or 2 sig figs, we have our 2 sig figs here. And round whenever it's necessary. This one does not need to be rounded because it's 0.020599. So it's not going to be rounded. We just keep it at 0.60. So anytime you calculate the pH of a strong acid, you got to pay attention to which acid you're working with, what the concentration of it is. So keep in mind this table is a really important table. Now here's a new table. So this table here is one we're going to practice with. So we're going to use a combination of these equations that we've looked at here in calculating this. Now the one equation that we have not looked at but similar is how to calculate POH. So POH is equal to negative log of the concentration of hydroxide if you know the concentration of hydroxide. If not, what we'll do is we will take the KW equation. So another equation here is where you have pKW. Take the negative log of that, we will get 14 is equal to the pH plus the POH. All right, so this is another, and this is a very useful and easy equation to work with. So going back to to the table here. So we're going to look at number 1. All right. So number 1 is where we have the pH given to you as 8.5. So we can go a couple different ways. So first, let's go ahead and calculate the concentration of hydrogen ion. So earlier we had the pH is equal to negative log of the hydrogen concentration. That does not solve for the hydrogen concentration, but what we do see is we have pH. That's a power function. So if you're given pH, what we need to do is we need to get out of the log function. To do this, we're going to do the anti-log. So the anti-log, if you look if you have a TI-83 or TI-84, if you look and you type in second log, what you will end up with is 10 to the x power. Now, in this case here, we did the negative log, so we're going to go backwards, and we're going to do 10 to the negative pH. So to figure out the hydrogen concentration, we're going to do 10 to the negative 8.5. And type that directly in your calculator, and you'll solve for that. And what you end up with is now this would be 1 sig fig here. So, but I'm just going to carry it out to 1 decimal place. We're not focused on significant figures in this example. But if we were, it would just be 3 times 10 to the negative 9. Now, that solves for our hydrogen concentrations. Next thing we're going to do is we're going to calculate the pOH. To do this, all we do is 14 minus 8.5, and what we end up with there is 5.5. To get the hydroxide concentration, we'd use the same equation, but this time instead of using pH, we'll use pOH. So we're going to do 10 to the negative pOH. So we can do 10 to the negative 5.5, and we get 3.2 times 10 to the negative 6 for that. Now, is this solution acidic, basic, or neutral? So the pH scale, if you don't know the pH scale, it ranges from 0 to 14, 7 being neutral, and then 7 to 14 being basic, and then below that is acidic. So always look at your pH here for this. So the pH is 8.5, so that's an example of a basic solution. Next problem here, we're going to have a pOH of 5.06. Let's go ahead and calculate that pOH by taking 10 to the negative 5.06. And what we get is 8.71 times 10 to the negative 6. To get the pH, we'll just do 14, subtract the 5.06, and that gives you 8.94. And then to figure out the hydrogen concentration, we do 10 to the negative 8.94, and we get 1.15 times 10 to the negative 9. I'm not paying attention to significant figures right here. If I were to pay attention to significant figures, all of these would be 2 sig figs. So this, we should have 8. Let's see if I can. There we go. So 8.7 times 10 to the negative 6 here, and then this over here would be 1.2 times 10 to the negative 9. So that would be the correct sig figs for that. So this is a basic compound because the pH is above 7. Now the last one here, we're going to go ahead and calculate the pH. So we're just going to go left to right. The first thing to do is calculate the pH. So we're going to take the negative log of 7.58 times 10 to the negative 3, and we end up with 2.12. So now this is 3 sig figs. So I'm going to keep the sig figs here. So 2.120 for the pH. Then we're going to subtract that from 14, and we end up with 11.880, and then we do 10 to the negative 11.880, and we end up with 1.32 times 10 to the negative 12 for the hydroxide. Now the pH is below 7, so this is an acidic solution. So that basically covers how we go about solving for the pH of a strong acid. In the next video, we're going to be studying weak acids and how to calculate the pH of a weak acid. Thanks for watching.